Welcome to Brain Vision.
In this question, we start off with a ramp. We have some crates that are coming down from the ramp at a velocity of 1.8 meters per second. That's the initial velocity. We are given that it travels a total distance starting from the head of the ramp all the way to the spring, right? At total distance of 8 meters. Well, this includes compression of the spring, right? So the spring initially is not compressed, maybe around here, and then it gets compressed by a certain value. And so we want to find what is the spring constant that will allow us to meet all these criteria. Well, we're going to use energy conservation. That is, the total initial energy must be equal to the total final energy. Right, total initial energy comes from the kinetic energy at the start of the ramp. Is half m times 1.8 square, and also the gravitational potential energy, right, GPE over here, which we will have to calculate from the angle, right, of the ramp. So mg times 8 sine 22 degrees. So this is the initial total energy. Well, the final total energy is of course we have the work done by the friction, right? We're given is 550 newtons times the distance, total distance traveled along the ramp, which is 8 meters. So this is the work done by the friction. We have the elastic potential energy that is stored, so that's half kx square, where x is the extension, right, of our spring. So with this equation, we can then solve for what is half kx square over here by substituting m to be equals to 1470, the weight divided by g, 9.81. Right, so mg is just the weight, 1470. From this, we should get half kx square to be equals to 248 joules. Now, but we are not done because there's two unknowns over here, k and x. We don't know what is x as well. So what we need to do is to use the other condition, right? We are given that the box, once it reaches the bottom, right, it should not, right, the bottom over here, it would not bounce back up the ramp. Now at the bottom of the ramp, it experiences a few forces. So we have the force coming in from the spring, F spring. We also have the static friction, Fs, static friction, and we also have the parallel component of our weight. Right? So the weight is downwards, but there's a parallel component, a small component of it, that is acting parallel to the ramp that will contribute to a downward direction as well. Now this downward direction force due to the weight, well, we know that this is the angle theta, 32 degrees. So this component must be the sine of the entire weight. And we know that the block cannot move, so the net force must be 0. So force from the spring is just kx. The frictional force we are given is 550 newtons plus the weight component, so mg times sine 22 degrees. Adding both of these together, we should get about 1 times 10 to the power 3. So about 1100 newtons. And now we are actually ready to solve for K. What we can do is we can square this value. And then we divide by 248. And we should get 2K equals to 4845. And so K must be equals to 2440, around there, newtons per meter.